before in Newton's first law, right, we're talking about forces that are balanced. In order to have balance, two or more forces have to add up to what?
0.
They must be 0, Lala. Yes, they must add to 0. No matter how many forces you have, even if it's at rest, you never say, oh, there's no forces because it's not moving. There's forces there that are balancing this object out or in balance with each other so that it doesn't move or that it maintains constant speed. Those are the two conditions of what we call equilibrium. Remember, the conditions of equilibrium is that the total force or net is equal to 0. Whatever the forces are, the total, you know, it has to be more than 1, because if you have one force only, it can't be balanced by anything else, so it's going to fly off in that direction. So if I push something in one direction, that's the only force acting on it, negligible air resistance, it's going to go in that direction. If I pull it the other way, it's going to come towards my unbalanced net force. So in order to have balance, we need at least two forces. So that speaks to Newton's first law and third law, because in this instance, the two forces are balancing each other. They're equal and opposite, which is Newton's third law, and they add up to 0. So it's first and third. So, you know, we have two laws happening at the same time most of the time, if not a lot of the time. So this is a state of balance where the object will be at rest or moving at constant velocity. They're both conditions of equilibrium or balance. That's why the first law of Newton, Newton's first law, is called the law of equilibrium or law of inertia. Law of equilibrium, okay, things are at rest or constant velocity. Law of inertia is a tendency to resist a change in your rest state or your constant velocity state. So it's either or, it's interchangeable terms, law of equilibrium or law of inertia, as we talked about yesterday. Okay, so now let me go and extend further, because number 28 actually applies to Newton's second law. So that brings me to this scenario. Okay, so and if it was Newton's first law, we'd have the forces. Let me just redraw that picture there. The force of the hand and the force due to gravity. Of course, these are, you make them as equal as you can, And my lines get a little squiggly because I'm trying to adjust the chair and screen here, but you get it. Okay, so these guys are basically the same, but opposite directions. Let's say that this will be 2 newtons going here. This is going to be -2 going down there. So you add them together, it's going to be equal to 0. So 2 newtons up, -2 newtons down. And so when you do this here, you're looking at the magnitudes of those forces, basically the size or the number of those forces. So 2 newtons -2, because 2 is here, -2 is there. And when you add them or add the negative of 2 newtons here, which is subtract, this is going to be equal to 0. Okay, fine. So this object's going to move up at a constant speed. So it's like, you're raising the guy up at a relatively constant rate of change of position, which is velocity, constant velocity. Or if you were falling down, like the skydiver case, so the velocity is going to be constant going the opposite direction. So if he's falling down, like say of a skydiver, we have the force of the air and force of gravity here, and he's falling down. So it's going to be a constant speed. That's why it's going to be kind of floating, coasting downward, cruise control down. Let's see. Yeah, and then also this really relates better with a parachute, because the parachute is going to basically take all the air going up. It's going to be balancing out with the force of gravity, and you're going to be coasting down to the earth as a skydiver. So either case. So now let's take this picture here and go to Newton's second law. So first law is about balance. Second law is about unbalanced or imbalance. So if I am now going to answer number 28, number 13 accurately, my hand force going this way is not going to be equal to my force of gravity. So now I have an imbalance in the forces. The force of the hand is greater than the force of gravity. So now I'm changing the velocity per time. That means I'm going to accelerate it upward. It's not going to be pushed up very quickly, or my velocity is going to change. And the same thing works with going the opposite direction. So the acceleration of the system is always in the direction of the unbalanced force, or the force that's larger than any of the other forces in the system. In this situation, the force of the hand is greater than the force of gravity. Therefore, the object accelerates upward. And if it was the either case, it would be downward. If I have now my hand going, down, the force of gravity would be greater than the force of the hand. The force of the hand would still be there, but it would just be a lesser value than the force of gravity. So Newton's second law deals with acceleration. Newton's second law of motion here. And let's see, there's a technical way of describing this, but I'm just going to give the equation. F net equals mass times acceleration, which means, and then if we, solve for acceleration here, just doing a little algebra, I'm solving for the unknown. I'm solving for A, and I'll divide both sides by M, and I get this equation, A equals F net over M, which basically means that the acceleration of an object, aka mass, the acceleration of an object or mass is caused by an outside unbalanced net force. That's one way to verbalize Newton's second law. The other way to say is that acceleration is directly proportional to the net force, which is inversely proportional to the mass. I don't want to use all that terminology, but basically what that last statement said is this equation. Acceleration is directly related to force, but inversely related to mass. So more massive objects have small accelerations. Diesel truck, 2 Newton force. Whereas a wad of paper, very small mass, high acceleration, 2 newtons, 0.0001 kilograms is going to have a high acceleration. You're going to be able to push that piece of paper under 2 newtons, but you're not going to be able to push that 2-ton truck under 2 newtons. Assuming that the net force is going to be the same, and we're using the same force for both objects to keep things simple. We're only changing one variable, which is the mass. So what we do anyway with experiments, we change one variable at a time. So this is basically Newton's second law, that no longer is the net force equal to 0, but it's equal to the object's mass times its acceleration. So to summarize in equation form, F net equals 0, second law. And we know that acceleration is a vector. It has a magnitude and direction as a number and a number and a direction. And that's equal to force, which is also a vector. So force depends on the acceleration. If there's an acceleration in the system, then we'll have an actual unbalanced net force. If I have a book on table, I have the normal force from the table. The table is pushing this guy up. Remember, normal force is the force that is perpendicular from any surface, up or down from any surface. And then we have the force of gravity. Let's say that it was on a table, but then I push it. Well, my pushing force is larger than any of these two guys here, so it's going to fly off in the direction of my push. That makes common sense. I mean, it's going to fly off in that direction, because now this is the state of imbalance. This is the unbalanced force that's going to produce an acceleration. So every time you have an unbalanced force, unbalanced net force, the object's going to go in the direction of that unbalanced net force. Therefore, you can figure out the net force in the system by multiplying its mass times its acceleration. So this F push is going to be ma. Whatever the book's mass is, multiplied by acceleration, which we either know either from graphical analysis, or it's given in a problem, or we can figure it out some other way, kinematics or something. And then once you find the acceleration, you can find the net force, which is going to be in the direction of the push. Questions?
Mr. Kelly?
Yes.
Could you scroll up for just a second, please?
No problem.
So just to the name, I forgot the name of the. Oh, okay, thank you.
Yeah. I guess I kind of don't hear you guys today, because I think I was playing around with my mic system, but I can hear you a little bit, but it's good. So there we have that, at least the introduction. You good?
Yes, thank you.
Okay, so the third law, let's see, is, I'm jumping into the last section. For every action, for every force in one direction, there is an equal and opposite force in the other direction. We've seen that already. So we've been implying Newton's third law all this time. That's all it is. So if I have an object on table, and for a free body diagram, you don't have to draw the other extraneous things, but I'm just giving this for visuals, such as context there, to let you see that the normal force is, yet again, perpendicular from the surface of the table and balanced by the force of gravity. Yes, this object's at rest. We have a condition of Newton's first law, but we also have a condition of Newton's third law, that the normal force is going to be equal and opposite to the force of gravity. That's Newton's third law. If I push on a wall, the wall pushes back on me, but the reason why you see me accelerating is because I have less mass than the wall, obviously, right? So Newton's third law there. So also on Newton's third law, it involves two objects and two forces. So if we're talking about this situation here, the scenario here, the force of the book on the table is going to be opposite. Well, let's say, in terms of the FG here, the force of book on the earth, all right, is going to be equal and opposite the force of the earth on the book. Two forces for direction. The magnitude is the same, but they act in opposite directions. So you can call them as two forces, because the earth is going to exert a force one way and the book is going to exert another force the other way, but opposite, but same value rather. And we had a question. Like a pendulum. Yes. I mean, that's slightly more complicated than what I'm talking about there, because the pendulum action has there's a part of gravity that drives the motion of a pendulum. So as the pendulum goes up to its apex on one side, we have a component of gravity that's going to drive it. So in that sense, in terms of your question, no, it's not like the pendulum, because we don't necessarily have an equal and opposite force from the component of gravity that actually causes the pendulum to move, because we'd have to include air resistance, which we normally don't. But if we do, then situation's more complicated. Yeah. So, but again, with any system, you can put a Newton's third law in there. It just depends on how you do it. So yeah, so this is what's going on here. Force of book on Earth is equal and opposite force of Earth on book. So again, we've answered 13 accurately, or number 28 accurately. This would be the accurate free body diagram there. This is the system of, two objects, hand and, well, mass. And subscripts, these are the agents, the subscripts here, FH for force of hand, FG force of gravity negative because it's going downward. And yeah, so any questions on Newton's second law? F net equals ma. We can figure out, once we know the force, we can figure out the acceleration. Once we know the acceleration, we can figure out the force, things of that nature. But going back to Newton's second, if we had a series of masses and we had a force scale, a Newton scale, I like to call it, and then we were pulling these successive masses of different masses along, we would get different readouts from this force scale, which is in the y-axis. And generally speaking, so we can't perform it, so we're just going to graph the data, arbitrary set of data. When we perform it, we will get a linear relationship between all of these masses. Say we have mass 1, 2, 3, 4, and force 1, 2, 3, 4. We get a successive rise in force for every mass. But we'll see that relationship is linear. And the slope of this line here will basically give us the constant acceleration for all of those masses and all of those forces. So the slope here would be the acceleration, the common acceleration for all those forces divided by mass. And that's one way that we can get Newton's second law derived. There's another set of pictures in this section that you can look about, but I just wanted to summarize and simplify all that data for our time in context of Newton's second law that we've been talking about so far. So accelerations, net force over mass, and we know that this is a slope equation because it's going to be rise over run, and the force is in the y-axis, so F net is in the numerator and mass is the denominator, and so the common slope would be acceleration in this case. So then when you solve for net force, it's going to be F equals mass times acceleration, because you're going to multiply both sides by mass to get your net force. And so that's just a roundabout way of saying the same thing. Okay, if you're following along in the text, talk a little bit about lesson 2, talk about weight and drag force. With drag force, we pretty much already talking about with the skydiver. We have air resistance coming up and the force of gravity going down. So that's all this so-called drag force is. But let's talk about weight. So lesson 3, weight. Weight is like a form of Newton's second law. That weight is going to be commonly called the force of gravity, which is equal to mass times acceleration of gravity. And I say it's a form of Newton's second law because we know Newton's second law is any net force equals to mass times any acceleration. Well, the acceleration in this case is going to be gravity. And so this would be called the weight equation. So when you stand on the scale, the scale is basically measuring the coupling or bringing together of the gravitational acceleration multiplied by your mass, and that's what you read on the scale, is this mg effect. Because when you stand on the scale, the normal force of the scale goes this way, and it's balanced by the force of gravity. So basically, the scale is reading this, the normal force that pushes back, which is equal to this, mass times gravity. So let's say, for example, in kilograms, my mass is like 77 kilograms, right? And multiply that by the acceleration due to gravity, and that will be my weight in newtons. And then you can convert that to pounds. You know the conversion scale. So I have a digital scale here at my place, and yeah, so it reads kilograms. I can set it to read kilograms or pounds, but in terms of what I do, what you guys are used to, kilograms is a nice way to see that. So when you multiply that, 755 newtons of force. That's the force due to gravity. That's my weight in newtons, and then I can convert that to pounds as necessary. So that's all weight is this equation. There's a condition called weightlessness in space. You're really not weightless. You're apparently weightless. What's going on is that there's two forces balancing themselves out, and you appear to be floating around. You appear to feel nothing because those forces are equal and opposite on you, that you don't feel anything one way or the other. That's what weightlessness is. You still have mass, you still can feel yourself, but you don't feel heavy because there's two forces operating on you that make you feel as though you're weightless. And that condition happens in space. Because on the Earth, you cannot ever feel that way because the mass, the acceleration of gravity, the force due to gravity is too strong for you to not feel some kind of heaviness, depending on how much mass you have. So I'm now on the comparing weights example of the weights section. See if you guys are all there. I would like to just read through this together. Let me know if you're not there. So I'm looking at this example. It says Kieran holds a brass cylinder in each hand. Cylinder A has a mass of 100 grams. We convert that to kilograms. And cylinder B has a mass of 300 grams. What upward forces do his two hands exert to keep the cylinders at rest? If he then drops the two, with what acceleration do they fall? Ignore air resistance. So that's a typical thing. We're going to ignore air resistance because for the most part, it doesn't really matter for this level of speed of objects. The object's not moving at a high enough speed to include air resistance or make air resistance relevant. So there's, in order to keep the boxes at hand, the force of his hands act upward, right? To balance out the force of gravity. And they give you little problem solving conditions there. So we see the force of hand on A, force of hand on B. All they want you to do is figure out the weight of both cylinders, which is mass times gravity, this equation you see right here. That's all that's going on. So technically, in terms of the magnitude, which I'll elucidate further, the force of gravity is pointing down, but which is correct, of course, because as we see here, Fg is negative, and that's why they have the negative there. And so we get an answer of 0.98 newtons. Well, it's going to be 0.98 newtons down and 0.98 newtons up for a sum of 0 to keep the guy at rest in both hands, right? And so we do the same thing for cylinder B, mass times acceleration of gravity in newtons per kilogram and meters per second squared. Same thing, 2.9 newtons up. So those are the forces. And so after you get the forces, you can figure out the acceleration quite easily. And we know that F net is equal to ma. Or in this case, the A is G, same, right? The acceleration will just be force divided by mass, as you can clearly see there. And we have the force already from the previous steps divided by the mass, and you get 9.8 meters per second each time. So it doesn't matter what mass you are. Gravity is going to act on you equally. This is something we've played around with, we've discussed before. Gravitational acceleration is irrespective of mass, whether it's at different heights or whatever. The time will be different to fall down, the velocity as well, but the acceleration constant. Because this is the strength of the field of gravity as pertains to the center of the Earth. With a larger mass like Jupiter, that acceleration would be much larger. And we'll see later on with Newton's law of universal gravitation why that's the case. You know, when we get to that subject, because this is the gravitational field on the Earth. There is a universal gravitational constant that relates to any mass, any two masses, whether it's two erasers or two black holes. And black holes is a little different because it's relativistic, but two planets. So yeah, let's do that first one, right? Are you guys there at practice problems number 1, additional practice? You place a 4 kilogram watermelon?
Yes.
Okay, awesome. So we place a 4 kilogram watermelon on a spring scale that measures in newtons, right? So we put that guy there and it says, what's the scale's reading? Anybody want to tell me what that is? How would I do it from what we've seen so far? I'm trying to, what they're asking for is the weight. Remember, weight is force due to gravity, mg. I got the mass of 4. What's gravity?
9.81 meters per second squared.
Right. And that's your weight. That's the scale. The scale is going to read roughly, whatever that is, 36, 37. Okay, 39. 39.2 newtons upward. So this is what's going to be read in newtons. In kilograms, it says 4. In pounds, well, let's do that real quick. So there's 2.2 pounds to a kilogram. Yeah, I believe that's correct. So the kilograms cancel. 8.8 pounds. That's what we're used to. So you can have your digital scale read in pounds. It's going to say 8.8 kilograms. It's going to say 4. And newtons, it would be 39.2. Those are all equivalent relative to the conventional concept of weight. Well, kilograms is not really a weight, it's a mass, but, you know, context. Any questions on that? Right? For question 2, it says you place a 22.5 kilogram television on a spring scale. If the scale reads 235.2 newtons, what is the gravitational field? Do we need to do anything for that question?
No, because we know that gravity is 9.81, right?
Yeah, that's right. So even though they give you all these fancy numbers, we know that the gravitational field strength is constant at 9.81. Exactly. Yep. So that's it. So that's the long and short of this weight drag thing. Apparent weight. Okay, we can do a quick example on that. But apparent weight is the weight that your scale reads. Weightlessness is a balancing of two or more forces. You still have mass, so you're still going to have some weight if you stop floating around in space and stand on the scale. Well, only if an artificial gravity situation, but yeah, you still have mass, so you still have weight. You just feel like you don't. I'm just going to float past this here. Drag force, okay, it's basically the upward force of the air, that results in something called a terminal velocity. So like again, I choose a skydiver example. So let's say that you have a parachute going on, and you have the air resistance going up, and your drag force or air resistance is going up, force of gravity. Those are balancing, so you're floating down at cruise control, aka terminal velocity. That's all terminal velocity is. Read more about that for details, but I just want to summarize that. And this is the situation of drag, terminal velocity, where the velocity doesn't change. It's going to be constant. I'll move my cursor around as if you can see it. But this is the page 41 of 197 on the textbook, or page 99. Because at first, you're going to start to speed up, but then once those forces, quote, catch up to each other and balance, you're going to float down. Only happens with the parachute. Okay, and then the last section we just talked about earlier is Newton's third law of motion. Is action and reaction. For every action, there's an equal and opposite reaction. This dog right here. So it's pulling. Okay, nothing's happening. So we have two objects. We have the woman and the toy, or woman and the dog. And the force of the dog goes one way, and the woman on the toy goes the other way. They're equal and opposite. So stand still, like tug of war. That dog's not giving, and that woman's not giving. You guys see that picture? Anybody else following in the textbook? You see what I'm talking about here? This woman and the dog.
Yes.
Yes.
Okay. Yeah. So again, it's just a visual picture of Newton's third. Again, we did the definition that for every action there's an equal opposite reaction, and here's the basic formula again. Two objects, two forces. So object A on B. So it could be anything. A force of A on B is equal and opposite B on A. And A and B could be represented by any two objects, of course. That's why we want to generalize things. And so they have this picture of the tug of war people. Newton's third law there. Okay, balancing, force of gravity. So I'm going to get to the picture of the people in the tug of war. So we have an interaction pair. We have, if we're just looking at the left side is pulling to the left, and at the same time, simultaneously, right side is pulling right. And then if we're looking at the right side, the left force is going left, and the right side is going right. But for every situations, every scenario, at least in this instant, the forces are balanced. They're equal and they're opposite. No one's moving until at some point somebody just plants their foot properly or feet properly and starts to unbalance the system and pull one way, and that team will win in the tug of war, because now that particular team has caused an acceleration for the other team to go in their direction. All right, questions on second, third law? Just giving you the summary of that. Again, these notes and everything else, I'll be grading everything, by this weekend. Just want to collect everything before we go to our next bit, which is the project and stuff. But I'll have things graded. Again, at the tail end here, it talks about the normal force. We know something about the normal force so far. That the normal force is that force that's perpendicular from any surface. It's just a summary of all of this stuff here. So we have a little 10 minutes remaining here. Let's see if we can do a few of these. A question from before. So I'm going to go back to maybe Newton's second law. Okay, well maybe I'll suspend that for the moment because I wanted to talk a little bit more about weight. Okay, so back to weight. So that was on my mind earlier. Again, so I want to stipulate something that the force due to gravity is going to be negative mg, because here this will be force due to gravity. And that's technically how you should say it, because you don't want to say gravitational force, because some big wigs in physics would get a little, snippy about that, because what is gravity in order for it to be a force? Because it's all, there's one perspective you can take. It's a relativistic or general relativistic perspective that gravity is not really some force caused by some particular agent, some particular particle or whatever. There's the graviton, so-called, hasn't been discovered yet. So we don't know exactly the source of gravity, if you will. So we therefore say the force due to it. But again, it's semantics, kind of trivial. But, context would say force due to gravity, right? This is the equation for it, force due to gravity, but weight, I said, is mg. So this whole thing is force due to gravity because it has magnitude and direction. It points down. This is the value, and it points down. But weight is just the scalar. You can never have negative weight. You can have a negative force due to gravity because it's pointing downward. Much like speed and velocity. Speed is the scalar. Velocity is the whole thing. Questions? You get that? That's really what I wanted to just summarize here. Let's see if we can do a Newton's second law question here, last 5 minutes. Okay. So let's look at practice problem. I'm on page 90, I believe it would be. It says additional practice. I'm looking at it as number 12, for you, a different number. But it's underneath solving problems using Newton's second law. That's where I'm looking at. I would like us to do number 12, or the first question. We have two horizontal forces. 225 newtons and 165 newtons are exerted on a canoe. If these forces are applied in the same direction, If these forces are applied in the same direction, find the net horizontal force on the canoe. In my book, it says dance. What? Typo. Okay, so I got this 225 and I got this 165. Who wants to tell me the net force? Somebody who hasn't spoken yet. Not the VIPs. The VIPs have spoken. Arthur, what you got? What's the answer?
$390.
I'm sorry?
$390.
Yes, we just add them up. Same direction, simple. Yes. So la. 390 newtons. Remember, force is measured in newtons. It's a rising newton. Okay, what about if they went in opposite directions? Let's say I did 165 here and then 225 there. What's the net force, and where and what direction does this object move? Anyone? What's the net force and where does the object move?
It moves to the left.
It would move to the left with 60 newtons, right?
Okay. So of course this is the negative direction because XY plane, negative. So let's see. So looks about right. Miles. So yeah. So negative 225 plus 165. That's 60. I'll take your word for it. All right. So negative 60 newtons. Yeah. Subtraction. It's trivial for odd reasons. Negative 60 newtons. So the net force is 60 newtons to the left or to the west. So the object moves west or left. Remember that the direction of the net force is where the object's going to go. So it's going to be pulled more to the left than the right. And vice versa. If I had 225 on the right and 165 on the left. So here's a little challenge question as we go off for the day. Well, let's say I had 165 like this and 225 like that. How would I get my net force? We don't have to get it, but how would you do the problem? Anybody? Anthony, got any ideas? Leah, Mark. If you had a situation like this, I had a force in the Y direction and then one in the X direction, how would I get my force? Quick answer, hint. It starts with a P.
Don't we get the components of?
I would use the P
Pythagorean. I don't know.
Yeah, well, that's the typical P theorem that we should be familiar with. We would use the Pythagorean theorem in order to get the net force, but we're not going to do that. We're done for right now. So again, no homework for Friday. Friday, we're going to come back and get back to put some of these dynamics into project and continue on with that. And that's it. Thank you guys. Have a good one and see you on Friday.